The moon has been in Earth's sky for 4.5 billion years. It rises, sets, pulls the tides. You've seen it your entire life. When Apollo astronauts brought back lunar rock in 1969, laboratories measured oxygen isotopes in those samples. Every planetary body has a unique isotopic signature, a fingerprint determined by its formation location in the solar system's dust disk. Mars has one. Meteorites from Vesta have another. Earth has its own. The moons matched Earth's exactly. Separate objects in the solar system don't match like that. If the moon formed elsewhere and wandered into orbit, its isotopes should reflect that origin. If it spun off from early Earth, the separation should have created differences. The moon also has almost no iron, less than 5% of its mass, compared to Earth's 32%, and it's abnormally large, 1/4 Earth's diameter. Identical isotopes, opposite iron content, impossible size. By the 1980s, planetary scientists had one explanation that fit. Earth and moon formed together from the wreckage of a collision that vaporized rock. In 1969, Apollo 11 astronauts brought back 21.5 kilograms of moon rock sealed in vacuum containers. Labs around the world analyzed those samples for years, measuring the ratios of oxygen isotopes, specifically oxygen-16, oxygen-17, and oxygen-18. Every planetary body has a unique ratio, a fingerprint determined by its formation location and the conditions in the solar system's dust disk. Mars has one signature. Earth has its own. The moon's signature matched Earth's exactly. That shouldn't happen. If the moon formed from a captured asteroid, its isotopes would reflect wherever it originated, likely a different orbit with different temperatures, different materials. If the moon spun off from a rapidly rotating early Earth, it should still show some compositional difference from the violence of separation. If Earth and moon formed side by side from the same cloud of dust, the moon should have the same proportion of heavy elements, like iron. It doesn't. The moon has almost no iron core, less than 5% of its mass, compared to Earth's 32%. Three facts refuse to align: identical oxygen isotopes, radically different iron content, and the moon's sheer size. Our moon is abnormally large relative to its planet. It's 1/4 Earth's diameter. Mars's two moons, Phobos and Deimos, are captured asteroids barely 10 miles across. Jupiter's moons are large, but Jupiter is enormous. The ratio makes sense. Earth's moon is a gravitational anomaly, too big to ignore, too weird to explain with gentle theories. By the 1980s, planetary scientists converged on a single explanation that fit all three clues. Earth didn't form alone, and the moon didn't form somewhere else. They formed together from the wreckage of a collision so energetic it vaporized rock. The hypothesis starts 4.5 billion years ago, roughly 30 to 50 million years after the sun ignited. The inner solar system was still a construction site. Dust in orbit around the young sun clumped into pebbles through static charge and gentle collisions. Pebbles stuck together into rocks. Rocks accumulated into planetesimals, objects a few miles wide. Gravity took over from there, pulling planetesimals into protoplanets dozens or hundreds of miles in diameter. This wasn't orderly. Dozens of these bodies orbited in overlapping paths, colliding constantly, merging or shattering. Proto-Earth, sometimes called Gaia in this stage, was the largest survivor in the inner region, spinning once every 6 to 10 hours under a thick, hazy atmosphere of hydrogen, helium, methane, and ammonia. The young sun was only 70% as bright as it is now, so the sky would have been dim, tinged orange or pinkish red from the atmospheric chemistry. The crust was thin, volcanic, and unstable. There was no moon. The night sky was black except for stars and the constant streaks of meteors burning up in the upper atmosphere. Proto-Earth wasn't alone in its orbit. About 150 million kilometers ahead, at a point exactly 60 degrees forward along Earth's orbital path, another protoplanet was growing. This was Theia, roughly the size of Mars, half Earth's diameter, about 10% of Earth's mass. It had an iron core and a rocky mantle, just like Earth. It formed in a gravitational pocket called a Lagrangian point. Lagrangian points are solutions to the three-body problem in orbital mechanics. In any system with two massive objects, like the Sun and Earth, There are 5 points where their gravitational forces balance perfectly, creating stable parking spots. The L4 and L5 points sit 60 degrees ahead and behind the smaller body in its orbit. Small objects placed there will stay there, orbiting at the same speed, held in place by the combined gravity of the two larger masses. Theia grew quietly in that pocket for millions of years, sweeping up dust and asteroids in its corner of the orbit. It was a Trojan planet, a companion that never approached Earth because the gravitational balance kept it locked at that 60-degree separation. But Lagrangian stability is delicate. As Theia accreted more material, its mass increased. The L4 point can only hold objects up to a certain size. When Theia became too heavy, the balance failed. It began to oscillate, drifting forward and back along the orbital path like a pendulum. Each swing grew wider. Gravitational perturbations from Jupiter or Venus, both far more massive than Theia, nudged it during close approaches. Eventually, one of those nudges broke Theia free. Once it left the Lagrangian point, collision became a mathematical inevitability. Theia entered what's called a horseshoe orbit, spiraling inward toward Earth with each pass. There was no escape trajectory, no stable configuration. The two bodies shared the same orbital space, and orbital space doesn't allow two planets. The approach wasn't instantaneous. Orbital mechanics dictated weeks or months of visible escalation. If you stood on proto-Earth's surface in a spacesuit, the air was unbreathable. You would have noticed a new, unusually bright star in the night sky. Over the days, that star grew brighter. Over weeks, it swelled into a visible disk. Over months, it became a sphere, a second world hanging in the sky. Tidal forces arrived before contact. Gravity weakens with distance, so the side of Earth facing Theia felt a stronger pull than the opposite side. That differential stretched the Earth. The rocky mantle, still partially molten from recent accretion, bulged upward toward Theia. The ground quaked continuously as the tidal bulge migrated across the surface with Earth's rotation. Volcanoes erupted in clusters along stress fractures. The thin crust, barely solid, cracked open in long rifts that leaked magma. Then, Theia filled the entire sky. The collision happened at approximately 4 kilometers per second, about 9,000 miles per hour. In cosmic terms, that's slow. Asteroids typically hit Earth at 20 to 70 kilometers per second. The relatively slow speed mattered. A faster impact would have delivered so much energy that both planets would have shattered into fragments, scattering into independent orbits, or falling into the sun. A much slower impact might have resulted in a glancing bounce, with Theia skipping off Earth's surface and tumbling away. The angle mattered even more. Computer simulations show the impact was a glancing blow, roughly 45 degrees off-center. A head-on collision would have merged the two cores completely and stripped away most of Earth's outer layers, leaving behind a larger but fundamentally different planet with no moon. A shallower angle, closer to a sideswipe, wouldn't have transferred enough energy to create a debris ring. The energy release was incomprehensible by human scales. The impact that killed the dinosaurs 66 million years ago delivered the equivalent of 100 million megatons of TNT. The Theia impact released 100 million times more energy than that. It was enough to melt the entire outer layer of both planets. Melting wasn't the right word. The collision didn't just liquefy rock, it vaporized it. Solid stone became superheated gas. The impact site reached temperatures above 10,000 degrees Celsius, hot enough to break molecular bonds and turn silicate rock into a plasma of ionized atoms. Both planets stopped being coherent solid objects. Their boundaries dissolved. The immediate aftermath looked like nothing else in the solar system. Recent computer modeling, led by researchers Simon Locke and Sarah Stewart, introduced a new category of planetary structure to describe it: the synestia. The name comes from syn, together, and hestia, Greek goddess of home and hearth, meaning a shared home. A synestia is what happens when a planetary collision delivers so much rotational energy that the molten remnants spin faster than gravity can hold them in a spherical shape. Earth and Theia's combined angular momentum was enormous. The impact not only vaporized material, but also set it spinning. The vaporized rock expanded outward under its own heat, forming a massive rotating cloud, but gravity still pulled inward. The result was a compromise structure, a donut-shaped torus of gas and molten droplets, with a dense core at the center where pressures kept material liquid rather than gaseous. For a period measured in hours or days, not years, There was no distinct Earth and no distinct moon. There was only this spinning cloud, glowing orange and red from the heat of vaporized silicates, surrounded by darkness. The outer regions of the synestia, where temperatures dropped below the condensation point, began clumping. Molten droplets stuck together. Larger clumps pulled in nearby material through gravity. One clump became dominant, sweeping up debris in its immediate vicinity. That clump became the moon. High-resolution simulations published in 2022 by Jacob Kegereis and colleagues at NASA and Durham University suggest the moon formed in hours, not the thousands of years predicted by older models. The debris ring didn't drift lazily into aggregation. The shockwaves from the impact created instant density variations, regions where material was already compressed, giving gravity a head start. The proto-moon condensed rapidly from the outer edge of the synestia, while Earth recondensed from the denser, hotter center. The synestia model solves the isotope paradox. In older models, where solid or liquid chunks of Theia's mantle were blasted into orbit and gradually clumped together, you would expect the moon to be a mixture. Some Earth material, some Theia material, with isotopic signatures reflecting both. But if both planets vaporized completely and mixed as a gas before separating, the final isotopic composition would be uniform. The moon and Earth are identical because they briefly became the same substance. As the synestia cooled, Earth's surface solidified first at the poles, where rotational forces were weakest, then gradually toward the equator. The moon, smaller and less massive, cooled faster. Within a few thousand years, both bodies had solid crusts, though the interiors remained molten for millions of years longer. Theia didn't survive as a separate object, but it didn't disappear either. Planetary collisions don't erase mass, they redistribute it. Theia's iron core, denser and heavier than the surrounding silicate rock, behaved differently during the impact. When the two bodies collided, Theia's outer mantle, the rocky shell surrounding its core, vaporized in the heat and became part of the synestia. But the core, compressed under immense pressure and less susceptible to vaporization, punched through Proto-Earth's crust like a cannonball through paper. It sank. This is called planetary differentiation in reverse. Normally, differentiation happens when a molten planet separates into layers by density. Heavy iron sinks to the center, lighter rock floats to the top. Theia's core had already differentiated. When it merged with Earth, it dove straight to the bottom, adding mass to Earth's existing core. This merger had consequences. Earth's iron core is unusually large for a planet of its size, about 3,500 kilometers in radius, making up 32% of Earth's total mass. Mars, by comparison, has a core that's only 20% of its mass. The additional iron from Theia supercharged Earth's internal dynamics. A larger core means more convective flow, more heat, and more vigorous movement of molten metal. That movement generates Earth's magnetic field through a process called the geodynamo. The moon, formed from the vaporized outer layers of both planets, inherited almost no iron. Its core is tiny, less than 350 kilometers in radius, barely 5% of its mass. The moon is made of the lightweight stuff that was easiest to blast into space, silicate minerals from the mantles and crusts of Earth and Theia. This compositional difference is the second piece of evidence supporting the giant impact hypothesis. The moon should be iron-poor if it formed from debris, and it is. Earth should be iron-rich if it absorbed Theia's core, and it is. For decades, scientists assumed Theia's material mixed completely with Earth's during the synestia phase. The isotopes supported that conclusion. Everything blended together before separating. But in 2023, a team led by Qian Yuan published a study in Nature that challenged the complete mixing assumption. They weren't looking for Theia. They were studying seismic data. When earthquakes occur, they send shock waves through Earth's interior. By measuring how those waves travel, how fast they move, where they bend, where they slow down, seismologists can map the internal structure of the planet in 3 dimensions, the way a CT scan maps the inside of a human body. Deep in the mantle, just above the boundary with the outer core at a depth of about 2,900 kilometers, seismologists had previously identified 2 enormous anomalies. These regions, called Large Low Shear Velocity Provinces, or LLVPS, are areas where seismic waves slow down significantly. One sits beneath Africa, the other sits beneath the Pacific Ocean. Each is roughly the size of a continent and hundreds of kilometers thick. The anomalies meant the material in those regions was different, either hotter or denser, or compositionally distinct from the surrounding mantle. Most geologists assumed they were plumes of unusually hot rock, remnants of ancient convection currents. Yuan's team ran computer simulations of the Theia impact with different parameters, different collision angles, different speeds, different compositions. They found that Theia's mantle, while mostly vaporized, wouldn't have mixed perfectly with Earth's mantle. Some of it would have survived as coherent blobs. Theia's rock was denser than Earth's rock, about 2 to 3.5% denser, according to their models, because it formed farther from the sun, in a cooler part of the protoplanetary disk where heavier elements condensed more readily. When Theia's mantle material sank through Earth's molten interior after the collision, the denser portions settled at the bottom, resting on top of the core. They didn't dissolve into the surrounding mantle because the density difference kept them separate, like oil and water. Over billions of years, those blobs remained largely intact, too heavy to rise, too distinct to fully mix. The simulations match the size, shape, and location of the LLVPs. The African blob and the Pacific blob are remnants of Theia's mantle. They are the corpse of the planet that hit us, buried 2,900 kilometers down, still sitting where they fell 4.5 billion years ago. This is the third piece of evidence. We can point to specific regions inside Earth and say that came from Theia. The collision nearly destroyed Earth. It vaporized the crust, melted the mantle, and turned the surface into a magma ocean that took millions of years to cool. But it also built the conditions necessary for life. The impact knocked Earth's rotational axis from nearly vertical to 23.5 degrees. That tilt is the reason we have seasons. Without it, the equator would receive direct sunlight year-round, creating a permanent band of extreme heat, while the poles would remain in permanent cold. The tilt distributes solar energy more evenly across latitudes over the course of a year. When the northern hemisphere tilts toward the sun, it's summer there and winter in the southern hemisphere. 6 months later, the orientation reverses. This oscillation creates habitable zones at higher latitudes and drives atmospheric circulation patterns that distribute heat and moisture globally. The moon, condensed from the Synestia's outer edge, formed close, only about 24,000 kilometers from Earth's surface, compared to 384,000 kilometers today. At that distance, its gravitational pull was immense. Tidal forces didn't gently raise and lower the oceans by a few feet. They created waves thousands of feet high, massive enough to scour continents. These megatides occurred every few hours as Earth's rapid rotation carried different parts of the surface beneath the moon. The violence had a purpose. The tides stripped minerals from exposed rock and dragged them into the early oceans. Phosphorus, iron, potassium, trace elements essential for biochemistry, all mixed into the water. The oceans became a chemical reactor, a concentrated soup of raw materials. Current theories of abiogenesis, the origin of life, depend on this mixing. RNA and DNA molecules require specific building blocks. The tides provided them. The moon also acted as a brake. Its gravity pulled on Earth's tidal bulge, creating friction that slowed Earth's rotation. Proto-Earth spun once every 6 hours. The moon siphoned off that rotational energy, transferring it to its own orbit. As Earth slowed, the moon drifted outward. This process continues today at a rate of 3.8 centimeters per year. Over billions of years, Earth's day lengthened from 6 hours to the current 24. A 6-hour day generates constant, violent winds. A 24-hour day allows stable weather patterns and calm atmospheric conditions. Theia's core, merged with Earth's, increased the total mass of iron in the planet's center. A larger core generates a stronger magnetic field. Earth's magnetosphere extends tens of thousands of kilometers into space, deflecting charged particles from the solar wind. Without that shield, the solar wind would strip away the atmosphere molecule by molecule, the way it stripped Mars after Mars lost its magnetic field 4 billion years ago. There are 8 planets in the solar system and hundreds of confirmed exoplanets. Most don't have large moons. Most don't have stable axial tilts. Most aren't habitable. Venus, Earth's near twin in size and composition, has no moon. It rotates backward, likely due to a different kind of impact, and its day lasts 243 Earth days. Without a large moon to stabilize its axis and regulate its rotation, Venus developed a runaway greenhouse effect. Its surface temperature is 460 degrees Celsius, hot enough to melt lead. Its atmospheric pressure is 92 times Earth's. It's hostile. Mars has 2 moons, but they're tiny captured asteroids, Phobos and Deimos, each less than 30 kilometers across. Mars's axial tilt varies between 10 and 60 degrees over timescales of millions of years because there's no large moon to dampen the gravitational tugs from Jupiter and the Sun. When the tilt is extreme, Mars's poles point nearly at the Sun, causing the polar ice caps to sublimate entirely and redistribute across the planet. The climate swings wildly. Life, if it ever existed there, would have faced unstable conditions. Earth's moon is 1/4 the planet's diameter. That ratio is unique in the inner solar system. The moon is large enough to stabilize Earth's tilt within a narrow range, 23.5 degrees plus or minus about 1.3 degrees over a 41,000-year cycle. That stability keeps climate zones predictable. The tropics stay tropical. The temperate zones stay temperate. Ice ages and interglacials occur, but they're regular, driven by orbital cycles rather than chaotic axis wobbles. The collision had to be precise. If Theia had been twice as large, the impact energy would have exceeded Earth's gravitational binding energy, shattering the planet into fragments. If Theia had been half as large, the debris ring wouldn't have been massive enough to form a moon of stabilizing size. If the collision had been head-on, rather than a glancing blow, Earth's crust would have been obliterated, possibly stripping away the early atmosphere. If the Theia had hit faster, both planets would have vaporized and dispersed into space. If it had hit slower, the 2 bodies might have merged without creating a debris ring at all. The impact angle, speed, and masses fell within a narrow range that allowed both destruction and creation. Earth is a chimera, part proto-Earth, part Theia. We're standing on a planet that cannibalized its twin, and that act of cannibalism made the surface habitable. The moon we see every night is a scar, a piece of both worlds torn off and reassembled. You know the moon exists. You've seen it. What you've seen is the remainder of the most violent day in our planet's history, close enough now to seem gentle, far enough to have given us time. The moon pulls the tides. The tides pulled the chemistry. The chemistry pulled the first replicating molecules from the ocean, and those molecules eventually looked up at the moon and wondered where it came from.